This is section 11.3, part 2. We're now going to look at an alternative method for calculating dot product. We saw that the product of the magnitudes times the cosine of the angle was a way of doing this. But we also saw that unless we have a very specific circumstance, finding that angle or the cosine of that angle, especially in 3 dimensions, can be quite difficult. So we're going to look for another way of finding dot product. In order to do this, we're going to make use of the law of cosines, which I'm sure you studied probably long ago in a trig class somewhere. Here's a review for you. If you have a non-right triangle such as this, and notice I've labeled this in the standard way, then a squared is equal to b squared plus c squared, which would be the Pythagorean theorem, but then the correction for it not being a right triangle, minus 2bc cosine of the angle A. We're going to rewrite this in a vector form. If I have 2 vectors, v and w, then this vector is going to be v minus w. Right? If you remember back from one of the early sections, if I took this vector and reversed it and put it at the end of that one, I would get that little vector there. So, the length of this side of the triangle would actually be the magnitude of w. The length of that side would actually be the magnitude of v. And then the length of this third side would be the magnitude of v minus w. The angle A, we're just going to call that theta here. And I'm simply going to rewrite this statement using the vector norms, or vector triangle that I've drawn over here. So let's see, a squared, that would be the magnitude of v minus w squared. B squared, that's going to be the magnitude of v squared, plus c squared, the magnitude of w squared, minus 2b, which is magnitude v, c, which is magnitude w, cosine a, which for us is cosine theta. All right, we're going to start putting in some specifics now. I'm going to make the assumption that v is going to be the vector v1, v2. W is going to be w1, w2. So if I were to rewrite this statement using this, this is now the magnitude of v minus w would be v1 minus w1, comma v2 minus w2 squared equals the magnitude of v squared, so that would be the magnitude of v1, v2 squared, plus the magnitude of w squared, and this last statement, let's take a good look at that. Do you recognize this? That's just our definition of the dot product, right? So I could actually rewrite that as negative 2 times the dot product of v and w. Remember that my goal right now is to figure out a formula for the dot product that doesn't depend on the angle theta. And I'm looking pretty good here. We could solve for this dot product, and the angle theta isn't mentioned anywhere. So we're on our way to finding a nice formula that doesn't require that I know the angle. We're a little ways away from there. We're a few algebra steps away from there. So let's go ahead and do the algebra. Let's see here. This would be the square root of v1 minus w1 squared plus v2 minus w2 squared, all squared. So I'm squaring that square root, which will make that pretty nice. Same idea over here. This would be the square root of v1 plus v2, both squared, all squared. And then finally, the square root of w1 squared plus w2 squared, all squared, minus 2v dot w. All right. Clearly we can go ahead and say every square root is getting squared, so I can just ignore those. And let's next actually square these out. We'll write out what we get. Squaring the binomial here will give me v1 squared minus 2v1w1 plus w1 squared. And then squaring that binomial, v2 squared minus 2v2w2 plus w2 squared. And on this side, just everything without the radicals. We'll just rewrite. All right, now that looks like a mess, but it's a lot better than we might initially think, because notice there are a lot of terms that are the same on both sides, and I could subtract them off. Right? I could subtract a v1 squared off of both sides. I could subtract a v2 squared off of both sides. And the same with w1 squared, and also with w2 squared. So what I have left is a lot simpler than what we had just a minute ago. That's it on the left-hand side, and the right-hand side I just have negative 2v dot w. All right, looking really good. We divide both sides by negative 2, we'll have a really nice formula for v dot w. v1 w1 plus v2 w2 equals v dot w. So here's a beautiful formula that does not require knowing the angle between those vectors. It just requires knowing the individual entries, right? The v1 and the w1, the components. That's the word I couldn't come up with there. So this is going to be a really useful way of calculating dot product. The geometry is much more complex if I went to 3 dimensions, but as we've seen so many times before, once we've established a pattern with 2 dimensions, we can usually easily extend it to 3 or even more. So here we go, w dot v, what we just said, it would be the product, w1 v1 plus the product of the second components, w2 v2. As you can probably predict, if we were going to do the same thing in 3 dimensions, we'd simply have a third term to add on. So we'll start out the same way. Multiply the x components, plus multiply the y components, plus, and here's the new one, multiply the z components. Right. If we happen to have a 4-dimensional, 5-dimensional, or even larger vector, we would simply continue that pattern. So let's find a few dot products. We have an A and a B. If we want A dot B, we're going to multiply the first components, negative 4 times 3, plus product of the second components, 9 times 1, which is going to give me negative 3. Let's do another one. V dot W, 4 times negative 5, plus 4 times 1, plus negative 2 times negative 8. So it looks like we're going to come up with 0 here. And remember what we said in that little theorem at the end of the last video. If the dot product of 2 vectors is 0, that tells us something. it tells us that V and W are orthogonal. If they're both in standard position so that they do intersect, they would be perpendicular. All right, one more. Here's R and T. This one, I'm going to notice that, like here the I's are missing, here the K's are missing. These are ones where it's a lot easier for me to think about them if I rewrite them using standard position notation. So I'm going to take a moment and do that so I don't mess them up. There. All right, so R dot T, I would have 0 times 2 plus 3 times -6 plus 7 times 0. So -18 is the only non-zero term in that one. All right, we're now going to move on to some applications of the dot product. And we'll now know that we've got 2 different possible ways of finding dot product, right? We know magnitude V, magnitude W, cos theta. We also have this new method. Depending on the way the information is presented in any particular application problem, you'll pick one of those 2 ways to evaluate your dot product. So we're going to start with the application to work, because that's where we started all of this. So we're going back to it. Work, remember, is force dot product with distance vector. And in part A, we have a force of 16 newtons acting at a 28-degree angle to the horizontal, pushes a box 25 meters along the floor. In this particular case, if we sort of imagine the situation, here's our floor, here's our box. The force is 16 newtons at a 28-degree angle. And we're going 25 meters along the floor. We know the magnitudes of both the force and the distance, 16 and 25, and we actually know the angle between them is 28 degrees. Again, just as a reminder, you would have to take this F and translate it so that they both started at the same point to actually see that 28-degree angle in there, but it is the angle between the 2. So in this particular case, to do F dot D, because of the way this is presented, we know the magnitude of F and the magnitude of D, and we know the angle theta. So we might as well use that method. It's easier not having to put together the actual components in standard position. So the magnitude of F was 16 newtons. The magnitude of D is 25 meters. And we were basically told that we have a 28-degree angle. If I just go ahead and use my calculator to multiply those together, I get 353.18. And that would be newtons times meters, or Newton meters. By the way, you may have also studied that Newton meters, another word for that is joules. You can certainly use that if you want to. All right, in part B, this time instead of describing the situation, they actually give us the force vector in terms of its components in standard position. It moves an object from this point P to this point Q, and we're told forces in pounds and distances in feet. So W is still going to be F dot D. But notice this time we have a 3-dimensional situation, and we don't know the angle between our vectors. So we probably don't want to use this form. Instead, we probably want to go ahead and get the standard position, the component notation. We already have F. It's 316. And to get D, We just need to turn that information into a vector. Terminal minus initial, right? So Q minus P to get D. 4 minus 1 is 3. Negative 1 minus 1 is negative 2. And negative 2 plus 5 would be 3. Now I can use our little shortcut that we discovered. 3 times 3 plus 1 times negative 2 plus 6 times 3. And it looks like I'm going to get 25 here. And in this case, it was feet and pounds, so foot-pounds. All right, we can also use the fact that we know two different ways to find a dot product to find an angle between vectors. So that's our next application. If I want to find the angle between two vectors, we know this equation or this formula for dot product. If I were to calculate the dot product on the left-hand side using our newest method, I know how to calculate the magnitudes. I could actually end up solving for theta in this equation. And that's going to allow me to find the angle between two vectors whose angle I did not previously know. So let's try it. Here's r and t, just a two-dimensional one. I know that r dot t is magnitude r, magnitude t, times the cosine of the angle that I'm trying to find. I'm going to do r dot t here just by saying negative 6 times 4 plus 1 times 2. The magnitude of r, square root of, I'm just going to square these in my head, 36 plus 1 times the magnitude of t, square root of 16 plus 4 times the cosine of theta. Negative 24 plus 2 would be negative 22 equals the square root of 37 times the square root of 20 cos theta. So negative 22 divided by the square root of 37 times the square root of 20 is cos theta. And we'll just use an inverse cosine on that. And I get 144 degrees, let's call that. Okay. Let's just, since this is two-dimensional, let's sketch that really quick and just see if it seems reasonable. There's 4, 2. There's t. Negative 6, 1. So there's r. And if you look at that angle in between them, it's definitely more than 90 degrees, right? 144 degrees certainly seems reasonable as an answer here. All right, let's do the same type of thing, but in 3 dimensions. We won't be able to draw this one very well, but we could still do the calculation. So we want the angle between W and V. And I'm going to rewrite my W as 305 and my V as 124. And we have W dot V is the magnitude of W times the magnitude of V times the cosine of the angle between them, theta being what I'm trying to find here. So I'm going to start by doing the dot product on the left-hand side as 3 times 1 plus 0 times 2 plus 5 times 4. Magnitude of W, square root of 9 plus 0 plus 25. And the magnitude of V, square root of 1 plus 4 plus 16. Just squaring in my head there, so I don't have to write down quite as much. And then that gets multiplied by the cosine of this angle that I'm trying to find. Left-hand side then is 23, is the square root of 34 times the square root of 21 cos theta. So there's cos theta. And again, I'm just going to use an inverse cosine. And that's about 30.6 degrees. Now, I can't check this one as easily. I mean, I guess I could work really hard and see if we could approximate the angle between those by a picture. But instead of doing that, since graphing in 3 dimensions is so much more challenging, let's just think about this one for a moment. These two vectors have all positive, at least non-negative components. So these vectors really are in quadrant 1, both of them. If both of my vectors are in quadrant 1, they can't possibly be more than 90 degrees apart. So at least that much I can say, yeah, something less than 90 seems reasonable. If I wanted to actually draw them, I could take the time and do so, but I think we're going to accept this one. All right, we'll look at a couple more applications in the next video.